Great, yeah, thank you. So I want to tell you guys about some ideas from effective field theory pertaining to geometry, which I believe has a very natural home in amplitudes. So let's just first make a very simple observation about scalar amplitudes. Namely, they can be written in this form here. They depend on two things: coupling constants and kinematics. Ruth Brito gave a very nice talk this morning, reminding us of the motivation of this community and to study simplicity in the amplitudes and find structure. And there's a lot of progress that's been made in the study precisely these properties of this part of the amplitude in the kinematics. And the setup is that you specified your theory, presumably a simple theory that you have some control over, and then you try to expose all the properties you can and maximize its simplicity. Here's one example. If you compute gravity amplitudes in the MHV sector, it can be captured to any multiplicity by Hodge's formula. I want to argue that there's also a separate direction that we can study amplitudes in, namely in this other part in the space of coefficients or coupling constant. And instead of zooming into a specific theory, you have to take a broader view of QFT and study classes of theories. Just to get some intuition of what this means, is if you look at the scalar theory with derivative couplings, you can write them in terms of two simple Mendelssohn variables, S and T, with some coefficients. But these coefficients are not just arbitrary numbers. They have some properties. In particular, these coefficients are Riemann curvature tensors of field space. This is the idea I want to exploit and explore further. And the point is that this way of writing the amplitude is generic for any scalar theory with derivative couples. So if you have, say, Galton bosons in the nonlinear sigma model, this is the amplitude. But also, if you study Higgs physics, the exact same term shows up in those amplitudes. Okay, so there's three parts of this which have motivated me in recent years, and I'll try to touch upon all three of them. The first is to expose the simplicity in this other part of amplitudes. But this geometry not only gives you a way to organize the amplitudes, it also gives you new relations between amplitudes that we can exploit using this idea of geometry. And lastly, and perhaps most importantly, these can be turned into a practical computational tool for more phenomenological applications. Okay, let's just lay the groundwork and explain what we're talking about here. So take a very simple theory, a scalar theory with an n number of scalars, which I've grouped into this phi I multiplet here. And if you write down the Lagrangian with all the interaction with two derivatives, you can write it in this way. So you have the propagator, the kinetic term, you have the 3-point, 4-point, 5-point, and so on. And all these interactions you can group into a single function Gij, which is now a function of fields. Now, I have not said anything special about this theory as of yet. I'm not assuming any symmetries or the other properties of it. But even so, there's something we can do to it. Namely, we can do a change of basis or a field redefinition. So a field redefinition is just you take your fields, you write them as a different combination of fields. And this is this field redefinition mirrors coordinate transformation in GR. Now, the terms we have in the Lagrangian, the derivative and Gij, they transform appropriately under these field definitions. And now you can see that this Gij has the transformation properties a two-index tensor, which will then interpret as our metric in field space. Now, this is not a new idea, but it goes all the way back to the 70s, which I think mirrors a lot of the things happening in this community. And then we're taking old ideas and reintroducing them into this modern perspective and trying to utilize them massively. So there's been a lot of recent work exploiting these old ideas of geometry of field space. Now, with our metric, we can then open our favorite GR textbook and compute descendant quantities like the Grashoppel symbol or the Riemann curvature. They have definitions here. They're just derivatives of this metric, as so. At this point, I haven't done anything. I'm just group some terms and derive some quantities. But to see how, all right, sorry, before doing the amplitudes, let's add fermions to the story as well. So we'll do scales and fermions right from the start. So how does fermions fit into this picture? So for the scalars, the metric was the coefficient of our kinetic term that defined our geometry. Now for fermions, we can assume that something similar is going to happen here. So we write down our kinetic term for the fermions. We group some function k, scalar fields in front. And then presumably this should have some relation of the metric that pertains to the fermions. But if we do a field definition of the fermions, we see that this k factor here actually mixes into this other term, this current, like fermion current, scalar current operator. So in order to define something which is closed under these field definitions, we need both. So that's the only wrinkle that the fermions bring about, that we need these two terms. But apart from that, the story goes through. And we can take these objects, find a extended metric for scalars and fermions, which has the right transformation properties under field definitions. You see that this now depends on this scalar metric and this omega plus minus, which is the fermion guys, and so on. And then we can again recompute the Krustalov symbol and the curvature. And this is an example of the curvature with two fermion indices and two scalar indices. There, so far, so good. And this is useful is because if we start to compute some amplitudes, we will see that these guys appear. So we have the first example from before. If you have, say, scalar scattering amplitudes derived from this Lagrangian, they depend on the kinematics and some coefficients. And this sum of the coefficient that multiply each kinematic variable is nothing but these geometric objects like the curvature we derived before. So we can do this computation two ways, using, say, just standard Feynman diagrams, and get a sum of coefficients out, or we could use the GR definition. And now this is not just an accident at 4 point. This happens to be true at higher points as well. Here I'm showing a 5-point scalar amplitude. They have, again, kinematics and some coefficients. And these coefficients are, again, geometric. There's the covariant derivative of the curvature shows up. Now, if we compute fermion scalar scattering amplitudes, the same sort goes through. Namely, we can compute, say, 4-point, 2 fermion to scalar amplitude. It depends on some kinematics, these spinner guys here, and some coefficients. And the coefficient is now the fermion scalar current, the curvature we derived before. Again, we do 5-point, 2 fermion, 3 scalars. It's the kinematics times some coefficients, which are, again, are geometric quantities. So this happens to all orders or all multiplicities. Also happens to all orders in perturbation theory. Here's one loop example where the scalar one loop amplitude now depends on some different kinematics, including the loop situation and some coefficients, but the coefficients are now just the curvature squared. And if we do a 5-point computation, again, there's some kinematics and some coefficients. Don't be intimidated by the expression, but the point is that all geometric, like all the terms in the coefficients are geometric quantities. Like, great. That's a sort of simplicity that the amplitudes has, without assuming anything about symmetries or the special properties. Now, the second thing that the geometry is doing for us is it's giving us relations between amplitudes. So this was something we, together with Cliff Chung and Julio Parmartinez, while we were at Caltech, derived a soft theorem for scalar amplitudes. I'll just state what the claim is, namely that the soft limit of a scalar amplitude is equal to the low point amplitude acted upon by the covariant derivative in sets. Okay, so how does this work? We had already computed some examples. So if you remind ourselves that 5-point and 4-point amplitude are written as so. If we then want to take the soft limit of, say, particle 5, if you did spend 2 seconds looking at the expression, you see that the first line here depends on momentum of particle 5, all these kinematic variables. So they just go to 0 in the soft limit. And what we're left with are these two terms, which is nothing but the covariant derivative of the low point amplitude in the space of couplings and depths. Now, this happens also, so the original derivation is supposed to be valid at all loops, as long as there's no issue with order of limits. And we did a one loop application of this recently. So here's the 5 points example from before. And if you take the soft limit of this one loop amplitude, you end up with the covariant derivative of the low point amplitude as well. This is supposed to be true at all multiplicity and all loops. Now, if we add fermions to the picture, the moral is still the same. So here we have our 5 point, 4 point scalar Fermi amplitudes. We can take the soft limit of a scalar particle, say pk, and then this term drops, and we just get this term back, which is nothing but covariant derivative of our low point amplitude as before. But crucially, this covariant derivative knows about both the scalar and the fermion geometry. So in order for this to work, you have to upgrade your notion of geometry to include both sets of particles. You can go and do more things. You can say, okay, let's get other limits, say 2 particles, momentum go to 0 at the same rate, make a double soft theorem. Then it becomes so the double soft theorem for scalars, you get this second derivative of the amplitude, which is what you would expect from, like, say, a Taylor series expansion of the amplitude. But you also get this second term, which is has this kinematic factor and the curvature. So now you see the curvature explicit in the expression. If you add this fermion to the story, the same expression holds. The only thing is, you again need to upgrade your notion of geometry, where this curvature now is a sum over both the scalar indices. So this depends on the 2 soft particles and a hard particle. And this hard particle can either be a scalar or a fermion. And they both get the particle and reproduce this formula. A bit more radical and say, take the soft momentum of 2 fermions to 0, not scalars, but fermions. Then there's a different soft theorem taken in this form, where you get this computation of single soft theorems plus this term above here. Again, you get this the fermion curvature out. And the only other difference is that you get this factor here, which is what's Manuel done before, gets replaced by this spinner bracket. But apart from that, it's the exact same expression. Good. I want to then show you a different kind of relation where geometry something novel, and this is thanks to double copy. Let me just remind ourselves about how the double copy story goes in the context of color kinematics. So the thing you want to do is you want to write your amplitude in this fundamental decomposition of kinematics times couplings. In this case, it's the color. And for this, you want to write it as a sum of a trilateral graphs. If you can then find a representation of the amplitude with the kinematics satisfy the same relations as the color factors, then you obtain a color kinematic dual representation of the theory. In particular, you need this symmetry properties and Jacobi entities to be holding for both. Then you can replace the color by kinematics, and you get a new theory out. In this case, you get a special Gaussian amplitudes. And this happens at high points as well. So if you have a 5-point amplitude, you write it as some color times kinematics. And in this case, if you want to impose the color factor, which is these 3 Fs and Jacobi, you can show that there's only one solution to this set of constraints, namely that the kinematic factor just vanishes. It happens to be true, like the correct amplitude for odd points. you get back the special Galilean all-time cleavage is also 0. So far so good. But how does this square with our geometry story that we've been telling so far? Well, if we look back at our amplitude at 4 points, it was now kinematics and curvature. So we can keep this CK duality, but replace color by curvature. And we can ask the same question: can we find a form of the amplitude where the kinematics mirrors the properties of the curvature? So at 4 points, it happened to be that the symmetry properties of this curvature are the same as these two f's. So all the minus signs when you flip A and B, for example, is shared by the curvature. And the Jacobi entity will become the Bianchi entity for the curvature. So we find the same solution for the kinematics, and we get back the special Galilean using this double copy. But the plot thickens when we look at 5 points, because now our amplitude is definitely non-zero. Well, as before, it was 0. But we can go ahead and ask the same question: how can we find an expression for the kinematics which has the same properties as the curvature? And they have all the same properties as our 3 f's from before, except 1. And this is under reflection. So if you have the 3 f's and you reflect this diagram, you pick up a minus sign. While if you have this covariant derivative of the curvature and do the same permutation, you pick up a plus sign. And this different sign allows you to find a non-zero solution to these sets of constraints, and you get a new curvature kinematic dual amplitude. And if you double copy it, replacing curvature by kinematics, you get this other theory, which is the general Galilean amplitude. So far, not folded into this paradigm of double copy. Good. And I want to spend the last minutes I have to show you some practical applications of these ideas. And one area where you want the theory which has scalar these ideas of geometry, and one such theory is the standard model. We have the Higgs field and the Goldstone bosons of the weak interactions, as well as all the quarks and leptons. So it's the perfect to use these ideas. And if you want to embed new physics effects into this theory, we can do this in a model-independent way by using an effective field theory. So what we do, this has all been mentioned this morning by Jasper, that you extend this standard model Lagrangian to include effective operators, which capture the effects of new particles that we haven't so far seen. And just to give you a flavor of what these operators look like, here's a sample of them from the dimension 6 Warsaw basis. So it's just some additional fields and derivatives. Now, the pipeline from computing new physics effects goes as follows. So you can start with some new physics model, which you have in your mind. Maybe these particles exist. Then, if they're heavy, you can match these particles onto the standard model EFT at the new physics scale. And then you have to evolve all your predictions from that high scale down to your scale of the measurements using the RG equation. And also, if you're doing low energy measurement, like in beam physics, you match it onto a new EFT where the Higgs and the gate bosons are not there, and so on. So this is like the pipeline. So there's 2 crucial steps: this matching, as well as this is running part. So I want to focus on the RG computation and show you how the geometry enters here. So this is just for those who I won't explain this in detail, but those who know, this is the way we're setting up the computation. We're using some effective action computation using the background field method. You have to expand the coordinates to keep covariance. But basically, you can capture all these effects systematically here. So this trace log term for all your one-loop diagrams, 2 loops, you get these guys, so on. And these like very it's really just some background of fields. So this captures all external gauge bosons. And these are the things we want to compute. This is capturing, in particular, the UV divergence and the RG equations of our EFT. Now, if you look at this, just this scalar loop, like so, Tufts showed that for a renormalizable theory, it can be captured in this very simple form. That the UV divergence of a generic renormalizable theory can be captured by these two simple terms, which looks like a mass squared and some f mu squared term, where these x and y's are functions of the background field. Now, if you have an EFT, it turns out you can use the exact same formula holds, but you have to upgrade your notion of this gauge field to also include the curvature. So the geometric extension of Tufts' formula is as follows. And now the problem of computing these one-loop effects is condensed down to an algebraic problem where you just your curvature, multiply these in this formula, and you get some expressions out. And this is also what we did. So just to show you that we did something non-trivial, if you then plug this in, specify your curvature for the standard EFT, you get this whole mess here of this is one particular RG equation for one particular Wilson coefficient that depends on all these things. And this is like popping out from this very simple formula. So if you do this traditional way, you have to compute all the diagrams with all the coefficients and one by one, making sure you're not making mistakes. But if you use this geometric formula, then like you're showing that it's experiment covariant, and then it's less easy to screw up. So doing the same thing for the fermionic loop, you have this expression. I just want to show you that this y mu here is now the fermionic valued curvature that we saw before. As well as these derivatives are the geometric covariant derivatives. And then you fill in again, you get some expression. And this is the result that we got here. And lastly, to like the last part of the computation is to do this mixed bosonic fermionic loop, which we did together with Shashan and collaborators. The formula is given here, where again this covariant derivatives crucially depends on the Christoffel symbols for the scalars, but also the fermions, which is kind of neat. And then the result. So let me summarize what I've been trying to argue for. Space of geometry is another whole sector of amplitudes that we can further explore, and it has all the properties that we like. It's simple, and if you use this lens of you can also discover new relations between amplitudes, both in soft limits, as well as this example in a double copy, and it's practical. It'd be really tedious to compute using everything, all your Wilson coefficients, but if you can keep it sort of generic and compact and geometric as well, and you hit expand at the very end, then that just saves you a lot of trouble. And I haven't time to tell you about this, but all this is extendable to gauge theories or gauge bosons. And for the future, there's still a lot of open questions. The field definitions that I've been showing you and exploiting are field definitions without derivatives. Now, the estimate is invariant in a much larger space of field definitions with derivatives. And it's an open question of how this can be understood geometrically. So we need to simply upgrade our mathematics to accommodate this. I think if we find the right language, then we can expose even further structure. There's still questions about the geometry, the double copy, like now what's the rules? How can this be generalizable? How far can it go? And can we then extend this set of theories where we want to study in detail to include these more general theories, like Goldman bosons with non-symmetric cosets are still very from this point of view. I'll end there. Thank you.